Welcome. We are now in the third lecture of module 5, that is heat integration of the process. In the previous two lectures, we learned some basic principles of heat integration of the process, how the hot streams in the process can be coupled with the cold stream so as to minimize the load on hot and cold utilities. And then we saw some important parameters of this coupling. One of the important parameters was the delta T minimum temperature difference between the two streams at any end of the heat exchanger which is coupling the streams. And then we saw how the capital cost as well as the operating cost varies with this important parameter delta T minimum. We also saw the construction of composite curves, the relative positioning of the curves, and then we saw how grand composite curve can help us identify the utility selection. Okay. Now, in this lecture we take ahead this theme and then try to learn the ways of estimation of the capital and total cost targets. Now, in addition to prediction of the energy cost of the heat exchanger network, if it would be useful if we can also consider, if we can also calculate or at least estimate to some extent to some accuracy the capital cost of the network. Okay. The principal components that contribute to the capital cost are first the number of units or the number of heat exchangers that make match between hot and cold stream, then the area of these heat exchangers, then the number of shells in this exchanger, okay. Then the material of construction, then the heat exchanger type, whether we have a floating head or fixed tube sheet exchanger, plate heat exchanger, so on and so forth, and then the pressure rating of these exchangers. Now, some of these aspects you are going to learn in other courses of NPTEL. For example, there is a special course of NPTEL on design of heat transfer equipment. There is also a course on heat transfer. So, in these courses you will learn some of these aspects, for example, like material of construction, heat exchanger type, pressure rating, etc. So, what we do is that we mainly make emphasis on the first two aspects, that is the number of units, the number of exchangers that we are going to use for a particular heat transfer process, and the area of these heat exchangers. Okay. Now, to estimate the number of units, we make use of the graph theory. Okay. We use the graph theory. Now, how graph theory helps us in estimation of the number of units? Let us see. Okay. Now, graph essentially is a collection of points. Now, I am showing you two types of graphs, okay, each of which has 8 points, A, B, C, D, E, F, G, H, and these points are connected by lines. Okay. So, the lines which are being shown, some of them cross, but basically they are not crossing, but you have to read the diagram in 3D. Okay. So, this is say graph 1 and graph 2, the same points are there, same 8 points, but these are connected in a different way as I am showing. The points corresponds to process and utility stream, and the lines to the heat exchange matches between the heat sources and heat sinks. Okay. Now, we shall define certain terms. Okay. This point I note the points correspond to process stream and utility stream. And the lines to the heat exchange matches. Now, let us define the first term, that is path. Path is a sequence of distinct lines that are connected to each other For example, in this diagram, the A, E, C, G and D, A, E, C, G, D. Okay. This is a path. Okay. The graphs form a single component if any two points are joined by a path. Okay. So, that graph forms a single component if any two points are joined by a path. Now, if you try to identify the components in the two graphs that we have seen, okay, we can say that in graph 1 there is single component because each of the 2 points is joined by any point in this graph is joined to another point and there is a single component. Okay. So, any 2 points are joined by a path. Okay. However, in graph 2 there is a distinct separation. For example, there is no connection between BC and FG or BG and FC, and therefore, the graph 2 has 2 components. Graph 1 has a single component structure and graph 2 is 2 component structure. Then we define a term called loop. Okay. Loop is a path that begins and ends at the same point. For example, in graph 1, B, G, C, E and B. B, G, C, E and B is a loop. Okay. Similarly, C, G, D, H, C is another loop. Okay. So, that point we note examples of loop. Okay. B, G, C, E, B is a loop. Then C, G, D, H, C is another loop. And then if you compare these 2 loops, then you will find that there is a link, okay, CG link. Okay. So, if you remove that link, then B, G, D, H, C, E, B is a complete loop. Okay. Removing the CG link between loops gives a third loop. that is B, G, D, H, C, E, B. From the graph theory, the main result that is needed in the present context, where we are trying to find out the number of exchangers required, can be found. Okay. So from graph theory, the main result in the present context that is the number of units can be found as follows, or number of independent loops n number of units is equal to S plus L minus C, okay, where n units are the number of matches between streams, S is the number of stream including utilities, then L is number of independent loops, and C are the number of independent components. Now, the final network design should be achieved with minimum number of units, that is quite obvious, okay, to keep the capital cost low. So, that point we note final network design should be obtained with minimum number of units to keep the capital cost low. And to minimize the number of units in above equation, L has to be 0 and C has to be maximum, because the number of streams that are there, S is a quantity which is given to us. So, it is not in the hands of designer, it will be decided by the actual process. Assuming L to be 0 is a reasonable assumption, because in a process all of the points will be connected by one or the other way. Okay. So, the number of independent loops will be 0. Okay. As we saw in case of this graph 2, where there were 2 components, okay, and then the number of loops were high. So, in a process having many streams that are coupled to each other, assuming L equal to 0 is a reasonable assumption. However, if the network has 2 components, then the heat duties for streams A and B must exactly balance the duties for streams E and F, and then the same holds for streams C and D and G and H. Okay. So, these are rather unusual. Okay. If you see the second graph, okay. Now, A and B are hot streams and E and F are cold streams, but there are two components. Okay, so B and C, E and A, F and G are not connected. So there is a separate component of AB, EF and separate component of CD, GH. In such cases, okay, A plus B heat excess should be equal to E plus F heat deficit. Okay, and same thing holds for CD and GH, but this is usually not possible. Okay. So, safest assumption for C, the number of components, is that just one component exists in the process. So, safest assumption for C is that its value is 1, that the entire process is a single component. Number of units become equal to S minus 1 for L equal to 0 and C equal to 1. Okay. So, the minimum number of units required in a heat exchanger network is 1 less than the number of streams in that particular network. Therefore, for a single component and loop free network, the minimum number of units can be predicted by simply knowing the stream population. So, that important factor we have answered. For single component and loop free systems, the minimum number of units can be predicted by knowing the stream population in that network. Now, as we saw in the previous lectures, the process is divided at pinch, okay, and therefore we have two regions, like one above pinch and one below pinch, and then we also saw in previous lectures as how heat transfer across pinch causes excessive load on the utilities. So, it is an inappropriate heat transfer. You cannot transfer heat, or you are not supposed to transfer heat across the pinch, okay, and therefore if the network does not have pinch, then that formula directly applies, n units equal to S minus 1. If the network is divided at pinch, then we have to apply that formula separately for above pinch and below pinch region. If the network is divided at pinch, then the above formula applies separately to above pinch and below pinch region. So, number of units is equal to S number of streams above pinch minus 1 plus S below pinch minus 1. So, we have answered the first question that we started with, okay, that we have to determine the number of units or matches between the hot and cold stream, because they contribute, they are one of the principal components that contribute to the capital cost. Now, the next task before us is to calculate the heat exchanger area target. Now, we haven't made the actual matches between the streams yet. Okay, we have only identified the pinch and we have the composite curves. Now, in such cases, how can we identify or how we can determine the exact heat exchanger area target? Okay. The composite curves themselves contain the necessary information to predict the network heat transfer area. To calculate the network area from composite curves, the utility streams must be included with process streams in the composite curve to obtain a completely balanced composite curve, basically the same procedure as we have seen before, but with inclusion of the utility streams. Okay, so that point we note that we have to calculate the heat exchanger network area without actually placing matches between the streams, that is very important, without actually placing matches between hot and cold streams. But with using composite curves. So, to calculate the network area from composite curves, we have to construct balanced composite curves with inclusion of utilities along with the process stream to obtain the balanced composite curve. Now, the balanced composite curves do not have the residual demand for utilities. Okay. Now, I am showing you here a typical example. Let us say we have two composite curves as follows, which are not of course balanced. Okay. So, this much is the hot utility requirement steam and this much is the cold utility requirement. And then we can identify here the enthalpy intervals. Okay. Whenever the curve changes slope, okay, we have addition or deletion of the streams, and then for every change, the point which changes the slope, okay, at every point wherever the curve changes the slope, we project that down and then identify certain enthalpy intervals. So, these are all enthalpy intervals. Right now, we have 1, 2, 3, 4, 5 and 6 enthalpy intervals. Okay, like that. We can make a reasonable assumption that the overall heat transfer coefficient is constant throughout the process, and then assuming a true countercurrent heat transfer, the area requirement for any enthalpy interval k for the vertical heat transfer, that means direct transfer from hot stream to cold streams, okay, we can calculate the area of the network. Okay. So, that point to note, assuming constant u, constant overall heat transfer coefficient, and also assuming truly countercurrent heat transfer, the area requirement for an enthalpy interval k for vertical heat transfer is A k is equal to delta H k divided by u into delta T L M for that particular interval. Okay. Delta H k is nothing but the enthalpy change over the interval k, then delta T L M k is the log mean temperature difference for that interval, and u is the overall heat transfer coefficient. Now, the total area of the entire network comprising of 6 enthalpy intervals as shown, 1, 2, 3, 4, 5, 6 intervals, total area of the entire network comprising of 6 enthalpy intervals is a network is equal to 1 by u. We assume overall heat transfer to be constant, heat transfer coefficient to be constant. So, that comes out of the summation sign. K runs from 1 to capital K. Let us say capital K is the total number of enthalpy intervals, delta H k divided by delta T L M k. Now, although this expression is rather straightforward, derived from the individual enthalpy intervals, okay, there are certain problems. The problems with this expression are that first of all, the overall heat transfer coefficients are not constant throughout the process. And then we need to make changes to this. Okay. Now, we know a basic relation in heat transfer is that 1 by u is equal to 1 by inside heat transfer coefficient plus 1 by outside heat transfer coefficient plus the dirt factor and conductivity, but for time being we ignore that, we assume only the basic equation, okay. And then we can now divide this particular expression, decompose this expression into expression that takes into account the variation in u, but it also takes into account the number of hot streams and cold streams. So, in any interval, okay, there is a delta t log mean, okay, and then what we do is that we calculate the heat duty on hot stream and divide by the film coefficient for hot streams. So, let us say hot stream, number of hot streams are capital I. So, I running from 1 to capital I, Q I by H I, where H I is hot stream. So, Q I by H I is the heat, the area contribution from hot stream plus summation J running from 1 to capital J, which are the number of cold streams, and then Q j by H j. Okay. So, this is how we decompose a simpler expression into a slightly rigorous expression that takes into account the variation in film coefficients. But still there is a problem of determining the film coefficient. First of all, I give you the notations so that you can use this formula, because we shall use this formula in our tutorials. So, Q I is the stream heat duty or heat duty on hot stream I, Q j is the heat duty on cold stream, then capital I, capital J are the total number of hot and cold streams in any enthalpy interval. And capital K is the total number of enthalpy interval. The formula that we just saw allows us calculation of the network area based on vertical heat exchange model if the film transfer coefficients vary. Okay. For large variation in film transfer coefficient, the above equation gives problems. Okay. In this case, the non-vertical matching may be required to achieve the minimum area. Okay. That means, let us say that we have in a exchanger, let us say we have enthalpy intervals like this. Okay. And we are making matches, directly vertical matches, but if the film coefficients of the streams vary largely, okay, then this kind of a match may not give us the minimum area. So, we may have to go for a cross match like this. Okay. This may give us the minimum area. Okay. So, those points we need to keep in mind while making the matches. Okay. Now, if the film coefficients vary largely, then the expression that we have seen does not give the minimum network area. Okay. In this case, the prediction of true minimum area should be based on linear programming. However, this equation still is a useful basis for calculation of the network area. Okay. Because if the variation in film coefficient is less than 1 order of magnitude, then the above equation predicts the network area within 10% of the actual minimum. That point we note. Okay. If the variation in film coefficient H I and H j is less than 1 order of magnitude, which is quite a large margin. Then above equation predicts network area within 10% accuracy. Now, the network design usually do not approach the minimum, as the true minimum designs are too complex, and then significant reduction in complexity requires a small penalty in the area. The area targets being predicted here are used for pre-design optimization of capital and energy trade of evaluation of the alternative flow sheets. Thus, the area prediction that is used here along with the capital cost data for exchangers have a considerable degree of uncertainty. Moreover, the capital cost predictions obtained from above equations are likely to be more reliable than the capital cost prediction for major equipment items. Okay, so, that point we note here, that area targets predicted are only for pre-design optimization. Okay. Area targets predicted, because we are not making one-to-one match, we are just finding out the area in a particular enthalpy interval there where there are many streams, many hot and many cold streams predicted here are used for pre-design optimization of energy and capital trade-off. Then the capital cost data, the area prediction used here along with capital cost data may have certain degree of uncertainty. Now, the only issue that we are left with are the sources of film coefficients HI and HJ. Now, there are many sources here. One can use the tabulated experience values, order of magnitude coefficients, which are listed in standard books such as Paris Chemical Engineering Handbook, tabulated values which are maybe order of magnitude accuracy. Then second is the heat transfer correlations, which are also given in different handbooks. And then we have also to account some dirt factor that is also based on experience. So, now we have seen as how we can calculate the minimum number of units and then a relatively approximate area target from which we can estimate the capital cost of heat exchanger network. Now, with this we move ahead to the pinch technology of heat exchanger network design. Now, we shall go for one-to-one match of the streams and then how we can have minimum number of units above and below pinch region. So, the pinch technology. For heat exchanger network design. We have seen before the principles of energy integration of the system, and then the capital energy trade off in the heat exchanger network. Okay. The major factor in the entire design was delta T min, which affected both the capital and operating cost. Increasing delta T min reduces the capital cost, but increases the operating cost, and vice versa. Okay. Now, to start with actual design of the heat exchanger network by placing matches, okay, that is left out, and that we will do now. Okay. The two costs that are combined, the capital and operating cost, to obtain the total cost, and the optimum point in the capital energy trade off is to be identified and corresponding to the optimum value of delta T min. Optimum value of delta T min is to be identified, and individual exchangers should not have delta T min less than that particular set value, should not have delta T at any end below delta T min. This is the constraint that we put. Okay. Moreover, we also have seen that there should not be two more constraints, that there should not be a process to process heat transfer across pinch. And then inappropriate use of utilities, that is, no cold utility has to be used above pinch and no hot utility has to be used below pinch. Now, these rules are necessary for design to achieve the energy targets, and then assuming that no exchanger has delta T min less than the given set value. Okay. Now, before we can have some more criteria which help us in identifying the overall exchanger network design, and that we shall see now. When we start making the design, when we start placing matches between the streams, we should have good initialization, which means we should start the design at a point which has maximum constraints. The process is divided at pinch. We shall demonstrate the strategy for this particular pinch technology or the algorithm of pinch technology with an example. We take the same example as in the previous lectures, the 4 stream data which I am writing for you now. Hot stream 1, supply temperature Ts 250 degrees centigrade, target temperature 40 degrees, heat capacity flow rate of 0.15, then hot stream 2, supply temperature 200, target temperature 80, Cp value 0.25, cold stream 1, supply temperature 20, target temperature 180, heat capacity flow rate 0.2, and then cold stream 2, supply temperature 140, target temperature 230, heat capacity flow rate 0.3. Okay. So, with this you can calculate the delta H or the heat content or heat deficit of these streams as minus 31.5, then minus 30, then 32 and 27. So, with this example we shall explain or we shall try to learn the technique of pinch design for heat exchanger network, but that we shall see in the next lecture.